All right, hey guys, I'll be doing a lecture today on divergence and curl. Okay, before we get started on what divergence and curl are, there's just some background information that we need to go over, which is the two different types of multiplying vectors, that being the dot product and the cross product. So the dot product is a way of multiplying the magnitudes of the vector. So what we do here is we multiply the magnitude of vector B by the reflected magnitude of vector A, or the x component, or whatever you want to call it. And then we're multiplying those, and we get some value, which is this. And that ends up actually being the same thing as if you just added up, or multiplied the components and added the multiplication of the other components. And that's just different ways of how to calculate the dot product. The cross product is similar, but a little bit different. The cross product, instead of outputting a value like the dot product does, it actually outputs a vector. So if you have A cross B, that is going to actually output a vector, and the special property of the cross product is that the vector that's outputted is perpendicular to both A and B, and the magnitude of this outputted vector has the same value as the area enclosed by the two vectors. And so that's why I wrote, that's why it says here, here's my vector, actually the product of my cross product, and here is how large my vector is. It's this exact area. So when we write it out, I have my magnitude of my outputted vector is the equivalent of just AB sine theta, similar to AB cosine theta. And instead of adding the components, I'm going to subtract them, and I'm switching some of them around.
Why is it AB sine theta on the cross product?
Oh, okay. So this right here, this height is B sine theta, right?
Okay.
And this length is A, so the whole area of that parallelogram is A times B sine theta, because it's just the base times the height. Okay.
The magnitude's like from the line, like you use the tip from the
exactly. And so if I took like a triangle from here, I could just cut it and put it here, and then I'd have a rectangle, and that would be dimensions A by B sine theta. And that's how I find my area. And so very important to pay attention to these two right here, because we'll be revisiting those later on in the lecture. Okay, that's good for this slide. Okay, so now I'm going to start talking about vector fields in general. So a vector field is essentially what it sounds like. It's a field, and I'm only going to be talking about vector fields in 2 dimensions, but else it would get too complicated. So in 2 dimensions, essentially what a vector field has a couple of properties. It has the point that the vector is on, and it has the point in which the direction the vector is pointing in. So the reason that we actually have 2 inputs, 2 variable inputs for our vector field, and it's still a 2-dimensional vector field, is that if I input my point x, y, I'm going to get some, let's just say I want to input the point 1, 1, and 1, 1 is like here, right? Well, that's going to be where I'm looking at. And then what I get out of inputting 1, 1 is going to be the vector, like where it's pointing, essentially. And so that's why I need to have 2 variables for my vector field, is I need 1 to my original point when I'm plugging in to find where I'm looking at, and 2 where the vector is actually pointing, because the vector has a tail and a tip. So I have 2 properties of that. And so this is just how you would write a vector field, essentially. You just have a function of x and y as your x component of your vector, and a function of x and y as your y component. And, this is a very special type of vector field. It's called the gradient, and essentially what this is it's basically says that the x component of my vector field is the x derivative, and the y component is the y derivative. And so that's what del f, del x, del f, del y represent, essentially. Okay. All right, so now I'll be moving on to divergence. So divergence is something where it's just a method of like explaining how much the objects or vectors or whatever you want to call them are moving away from a given point. So let's just assume that this is our center point up here. So if I wanted to have positive divergence, things are going to be moving away from my point at an increasing speed. And so this is what it's showing, right? I have smaller vectors, and then as you go out, the vectors become larger and larger. And negative divergence is just the the opposite, instead of moving out from my point, I'm moving in my point. So if I wanted to imagine this as like water flowing, water would be flowing away from that point. Whereas here, water would be flowing into that point, like a sinkhole, for example. And then finally here, we have zero divergence. And what that says is just like water, it's just something moving in is equivalent to something moving out. So if I had water moving through that area, there wouldn't be any change in the volume of water. It would just be moving in and out at the exact same rate. And so now, here's what all this represents. Okay, so we'll start with the positive divergence, right? So as we, if we are focusing on our center point, way out in the center of this, this shape here, right? If we increase our x, what happens to our actual x vectors? Well, notice how if we increase the value of x, the x component of my vectors become larger, right? So that's why this is what I'm saying. This is what it says here is that as you make a small step in x, the actual x component of my velocity or my vector or whatever is increasing or is greater than 0. Now we look at the y component. Well, the y, if we increase our y, notice how the y component also gets bigger. Whereas if we decrease our y, it gets bigger, but it gets more negative. So in either way, I'm either making it both more negative or both more positive, and so that means that the rate of change of my vectors are going to be greater than 0. Does that make sense?
Yeah, is the magnitude just like normally determined? Or?
Yeah, well the magnitude, wait, what do you mean?
How is the magnitude shown here?
Oh, okay, so the magnitude, like for a vector field, if I have an input for my vector, that's my point. And then my output is going to be where my vector is pointing. Well, my output, I might have a really large vector, or I might have a really small vector. And so that's just what it shows here is that it may vary depending on where you are.
Okay.
So yeah, in this case, the magnitudes are increasing as you go away from the point.
Okay. Yeah.
And then with this one here, with negative divergence, it's actually it's actually notice how the magnitudes of the vectors are decreasing. So if I move in my x direction, so if I move to the right from my center of what I'm looking at, right? If I move to the right, notice what happens to my x components. They get smaller and smaller. They get more negative, right? Or sorry, yeah. Notice how here. So my x component initially is they get more positive. Sorry, notice how it's initially to the left, right? And then as you move to the left or the right, notice how they're going to change. So if I have here, my initial x is going to be pointing to the right. Now if I move my x to the right, now all of a sudden the x components of my vectors are pointing to the left. So notice how, so I'm on the left of my point here, right? My x components are pointing this way. All of a sudden if I change my x and I increase my x, all of a sudden my vectors are going to point this way. Same thing, so that's what it says here is that if I change my x, the actual, the x component is changing as well. So that overall ratio is going to be less than 0. Same thing with my y. It's exactly the same thing. And with here, the 0 divergence, essentially what this says is that like whatever I do with my x or y, that's going to create no change whatsoever in the magnitude of the vectors, like as you can see. And so what this says here is, so the actual formula for my divergence is simply going to be this. I'm just going to have the rate of change of my x component, my vector, right? That's p of x, y. It's going to, as I change my x, I'm going to be changing my x component. Plus, as I change my y, I'm going to be changing my y component. So, so here. So for example, let's just take a look at this one right here. So in order to determine whether I have positive divergence, right, I'm going to be looking at whether this addition, this value is going to be negative or positive. So here, let's look at the change in my x component of my vector with respect to x. So if I increase x, my x component increases as well. So that's going to be greater than 0. If I increase y, right, if I increase y, my y component is going to change. So that's going to be greater than 0 as well. So it's going to be, they're both going to be greater than 0, so they're both going to have a positive value or positive divergence. And sometimes it may be differing, like sometimes you might have vectors pointing in and out of the area, and then you would have to really see whether it's positive or negative by actually calculating the value. Oh wait, one more thing. No, and so this is essentially just another way of thinking about it. So instead of saying, okay, I'm going to write del p del x plus del q del y, I'm going to write my divergence of v is going to be, remember the gradient vector field is the rate of change of f with respect to x plus, as your x component plus rate of change with, and the rate of change of y. And so essentially it's the dot product, right? Is I'm just going to multiply the rate of change with respect to x with times p, which is this part. And I'm going to multiply the rate of change with respect to y times q, which is this part. So the divergence is actually just the dot product, essentially, of like a partial derivative vector field. All right. So now this is where it gets a little bit weirder. So instead of having like objects moving in and out, we can also have objects kind of swirling around a given point. So if I look at this, you can see that my vectors are kind of turning around in a counterclockwise fashion around this little point in the middle here. So if they, so that's just what curl is, right? So curl just tells us how much is the vector field rotating around a given point. And so if curl is positive, the vector field is going to be rotating in a counterclockwise fashion. If it's negative, it's going to be rotating in a clockwise fashion. Just like if I have my angles, I always calculate my angles rotating counterclockwise instead of clockwise. And again, I just have some arbitrary vector field x, y, as a function of x and y. Okay, so here's what we need to look at now, is how to actually figure out whether it's positive or negative by looking at the rates of changes with my x and y values. Okay, so let's just say I want to increase my x right here. What happens to my, well, let's just say I center around this point. I'm just going from left to right, and I start here. Well, if I want to increase my my x, what happens to the y components of my vectors? Well, initially the y component is really, really small. And then all of a sudden it becomes larger and larger, right? You see how it's super small here, and then way over here it's much larger. And so what that's saying is that as I change my x, my y component of my vector is going to be increasing. So the overall, this value, this is exactly what I said, this value is greater than 0 in this case. Now, what happens if I move up and down in the y direction? What happens to my vector then? So let's just say I start from here and I move up. So right now, well, what happens to, if I move up and down, what happens to my x component of my vector? Well, my x component of my vector starts off fairly large, and notice how it basically, or I'll start here. Notice how it essentially is getting smaller, right? Over here, it's really large. All of a sudden, as my vector starts pointing downward, it gets smaller and smaller and smaller. And so that's going to be less than, this entire value is going to be less than 0. As I increase my y, my x component of my vector is going to decrease. And so with positive curl, this is greater than 0 and this is less than 0. And so my actual formula for curl is essentially, I'm just going to subtract the two. And notice how this is extremely similar to the cross product that we saw in the beginning, where I'm kind of flipping the components and then subtracting them instead of just adding them and multiplying them with the dot product. All right, that's essentially it for this slide. Yeah. Okay, and then finally, for some applications for divergence and curl, a major application for this in evaluating vector fields is looking at fluid dynamics, like how is fluid going to flow, and you can model that using vectors, right? If I know that I have some piece of some object or some fluid way over here, I can kind of see what the path is going to be over time, right? I can see just by looking at my vectors in what direction they're pointing.
Or like air currents or...
Yeah, air currents, exactly. Any sort that's like moving and there's kind of a uniform motion in certain areas. And then also there's, it's also really useful in force fields and calculating work. So for example, if this was like a force field, like whether it was like gravitational field or electromagnetic field, and I wanted to move an object through that field in any sort of path, like let's just say it's this path, so it's this weird parametric curve, I can actually calculate the work done on that object going through that force field by using what's called a line integral. And so these are all different applications of divergence, curl, and just the concept of vector fields in general. And one really important thing to note is that the divergence is the dot product, and the curl is the cross product. And so that holds true for 3 dimensions, but the only reason I didn't do that today was that it would take up way too much space because the curl formula, especially in 3 dimensions, becomes kind of messy. So it's a lot easier to visualize in 2 dimensions. Does that make sense? Okay. Yeah.
Which was ideal with this one, just that like, this is like the force that's exerted at each point in the electric field, and then as you move through it, then this
Yeah.
is like,
And so essentially, like to find your net work, right, you're going to sum up all of the forces times the change in position. And so it's going to be an integral. It's going to be a single integral of some parametric curve traveling through that field, essentially. Yeah.